In this session, we are checking what is memory bottleneck, how cache memory solves this issue, and the detailed working of cache. Imagine you are building a car that can blaze down the road at lightning speed. But here's the catch. Every time it needs fuel, you have to stop at an old slow pump that barely drips gas. Your high-speed car ends up spending more time waiting for fuel than actually driving fast. Frustrating, right? Well, this is a lot like a problem in computer architecture known as the memory bottleneck. In the early days, a scientist named John von Neumann designed an elegant, simple model for computers. This model used a single type of memory, RAM, to store both the instructions and the data needed by the processor. At first, this worked beautifully, like our speedy car on an empty road. The processor simply fetched data or instructions from RAM whenever it needed to. But as processes got faster, this setup began to struggle. RAM couldn't keep up with the process's demands, and suddenly our once efficient design turned sluggish. The processor, now much faster than memory, would sit idle, waiting around for data and instructions to trickle in. The memory bottleneck problem became a big challenge for computer engineers, sparking an era of innovation to find ways around it. Next, how we can solve this puzzle. Imagine constantly walking to the kitchen for a sip of coffee every time you are working. It's time consuming and interrupts your flow, right? But what if you could keep a mug on your desk right beside you? That's exactly what cache memory does for the processor. It brings frequently used data closer so the processor can quickly sip what it needs without trekking back to main memory. Cache memory was designed as a small, super fast memory unit that could store frequently accessed data. Instead of waiting around for RAM, the CPU could pull the data from the cache, keeping everything running smoothly. This was like putting a high-speed fuel pump right beside our fast car. Now, how does the cache memory work its magic? Let's break it down. To solve the memory bottleneck, designers focused on a key idea: reduce memory access time to keep pace with the processor's speed. Building ultra-fast memory for the whole system was way too expensive. So, engineers came up with a smart solution using the principle of locality. Principle of locality includes temporal locality and spatial locality. Moving to first one, temporal locality. When a program accesses a piece of data or instruction, it's likely to access it again soon. Imagine a loop in code. Those instructions are reused over and over, right? Next, we can move to spatial locality. Programs tend to access data stored in neighboring memory locations. For example, when one memory address is accessed, it's likely that nearby addresses will also be accessed soon after. These patterns, reusing data and accessing sequential memory locations, make cache memory incredibly effective for speeding up program execution. It's like keeping not just your coffee cup, but also a few extra snacks close by on your desk. Now, we can check features of cache. As mentioned, small, high-speed memory. Cache is much faster than RAM, though smaller, typically a few megabytes compared to RAM's gigabytes. Next, storing recent data. When data is fetched from RAM, it is also copied to the cache along with nearby data. This way, if the CPU needs it again soon, it's right there in the cache. Third point, efficient data replacement. Since cache is limited, older data that has not been used recently gets discarded to make space for new data. This approach allows the CPU to bypass the slower RAM for most operations, giving it the steady data flow it needs to perform at top speed. Now, we can delve the working of cache memory. When your computer needs data, it follows a three-step process. First one, check the cache. The CPU first checks if the data is already in the cache. If it is there, it is called a cache hit. Now the CPU can access it instantly, saving precious time. Second one, fetch from RAM if needed. If the data is not in the cache and is noted as cache miss, the CPU retrieves it from RAM at slower speed. This takes longer, but ensures the CPU gets what it needs. Last, the third step. Update the cache. After retrieving data from RAM, the CPU copies it and the next few nearby data points into the cache. If the cache is full, older, less used data gets replaced. In a way, cache memory is a bit like adding gears to a car, allowing it to operate at different speeds based on the road ahead. The memory bottleneck taught us that even the fastest systems are only as efficient as their slowest part. A valuable lesson in both computing and life.